let us discuss this important theorem of a scalar field. See, in this theorem, what have they given? We have two functions, f and g. Both of them are scalar field, and both of them are defined from S to R. Getting S is the non-empty subset of Rn. So the important thing is that given thing is f and g, both of them are differentiable at A. And our target is to prove that f plus g is also differentiable at A. Okay. For our regular derivative, we have done this theorem, we have discussed its proof, but for scalar field, we are discussing it at first time. Okay. See, there are two different ways to prove this theorem. There are either you can go with a definition involving limits or using epsilon delta definition. So I am going to prove this theorem using epsilon delta definition. So obviously at the beginning of proof of this theorem, I should take one epsilon. So let epsilon greater than 0 be given. So we have two simple information, f is differentiable at A and g is differentiable at A. Okay, so let us start with the first information, f is differentiable at A. We have f is differentiable at A. So you know the definition of differentiability. F is differentiable at A, therefore there exists a linear transformation. Therefore there exists a linear transformation T1 from Rn to R, and for above epsilon already we have assumed, there exists delta 1 greater than 0 such that you remember the definition is norm h less than delta 1 implies mod f of a plus h minus f of a minus t1 of h divided by norm h less than epsilon. Getting? So this is definition of differentiability I wrote. See, instead of epsilon, just for adjustment, I am going to take epsilon by 2. I will call it as this expression number 1. Okay. So we use the first given information, that is f is differentiable at A. As well as we have one more important information is g is also differentiable at A. So let us write that thing. We have g is differentiable at A belongs to S. So g is also differentiable at A. So again I can use the same type of definition and write. So therefore there exists a linear transformation T2 from Rn to R, and for above epsilon greater than 0 there exists, I will take delta 2 here. We have already called it delta 1 here. So delta 2 greater than 0 such that I am going to simply write definition. You can also tell me using definition what can I write. So norm h less than delta 2 implies mod g of a plus h minus g of a minus t2 of h divided by norm h less than epsilon. Again for adjustment, instead of epsilon I am going to take epsilon by 2. This is expression number 2. See, but actually first expression is true for norm h less than delta 1 and second expression is true for norm h less than delta 2. But we want both should be true simultaneously. For that purpose I am going to take minimum of delta 1 and delta 2. So then both of them will be true simultaneously. So we take delta is equal to minimum of delta 1 and delta 2. Okay, so then therefore for this delta we can use expression number 1 and 2 simultaneously. Okay, so there is no more space to write, so I suggest you to make a screenshot of it. After that we will go further. See, now we define a linear transformation T, okay, which will work for that f plus g. So let us define. We define a linear transformation T from Rn to R as, see, I am defining this way, T T of h is equal to T1 of h plus T2 of h for all h belongs to Rn. So in this way I have defined. Our definition of T is very simple, T1 plus T2. So now I will prove that this T is a required total derivative of f plus g, and in this way we can easily say f plus g is also differentiable at A. So let us prove it. So consider, I am going to consider norm h less than delta. So already I have told you, so delta is minimum of delta 1 and delta 2. So that's why expression number 1 and 2 both are simultaneously true for this delta. Okay. So let us consider what we want actually. F plus g of a plus h minus f plus g of a minus t of h whole divided by norm h. See, what we supposed to prove, we have to prove that this is less than epsilon, then we can declare f plus g is differentiable at A and t is a total derivative. Okay, so our target is to prove that this is less than epsilon. So let us simplify it first. So this is equal to mod f of a plus h plus g of a plus h. Okay, here also what can write f of a, but see there is minus sign outside, so that sign will get changed. Minus g of a, t of h means, you know, t of h means t1 plus t2 of h, right? Whole divided by norm h. So this is equal to, what will I do? F of a plus h, I will collect f terms of f minus f of a and this minus t of t1 of h, plus as well as we have this g of a plus h, g of a plus h, okay, minus g of a and this minus t2 of h, right, whole divided by norm h. So you know that if you take separate mod, value will get increased. So that's why this is less than or equal to. What I'm going to do, I'm going to take separate mod as well as I will divide separately each of them by norm h. So what will happen? Mod f of a plus h minus f of a minus t1 of h divided by norm h here, plus here also I'm taking separate mod, no? So that's why I wrote that thing, g of a plus h minus g of a minus t2 of h divided by norm h. But you remember that expression number 1, it says this is less than epsilon by 2. So this is less than epsilon by 2, and expression number 2 says this is less than epsilon by 2. So this is less than epsilon by 2. I will clearly mention from 1 and 2. So epsilon by 2 plus epsilon by 2, it is epsilon. Yes, we succeed in proving this is less than epsilon. So that's why directly we can declare f plus g is differentiable at A. So there is no more space to write. So make a screenshot of it. After that we will go further. So in this way, using epsilon delta definition, we proved the function f plus g is differentiable at A. Let us write it. So therefore, f plus g is differentiable at A belongs to S and its total derivative is, see, its total derivative we denote in this way, d of f plus g of A. Its total derivative is nothing but t, the linear transformation which we defined, getting? So this is equal to t of h, but t of h, definition of t was t1 plus t2, so t1 of h plus t2 of h. But you remember t1 means total derivative of function f and t2 means total derivative of function g. So this is nothing but d f of a plus d g of a. So that is we can write d f plus g. Okay, actually we supposed to write h here and here of h and of h. So d f plus g of a is equal to d f of a plus d g of a. Actually this is true for all h belongs to Rn. So in this way we proved that total derivative of f plus g is equal to total derivative of f at a plus total derivative of g at a. Okay, so our proof is over here. You can make a screenshot of it. After that we will stop. Thank you. Bye bye.